Dear students, let's continue our practices on mathematical analysis 1. So today's topic is limits of elementary functions and fundamental limits. So let's consider the first example. Evaluate the following limit: tangent x or sine x as x tends to 0. So, in order to evaluate and determine form 0 over 0, because here we have 0 over 0, if you put 0 instead of x, the numerator is 0 and the denominator also 0. And then we need to select and cancel common infinitesimal factors. We consider the last topic, infinitesimal factors. This is infinitesimal function. It is when function tends to 0, the function f of x we call infinitesimal function, and in the numerator and denominator. In this case, so we get sine x or cosine x, because tangent x is equals to sine x or cosine x, and times sine x in the denominator, and they are cancelled, sine x and sine x, and we have 1 over cosine x. And by the properties of the limit, we can write 1 over limit as x tends to 0 cosine x is equals to 1 over 1, because cosine 0 is 1, and the answer is 1. The next one, evaluate the following limits. So here we deal with an indeterminate form, infinity minus infinity, because if you put 1, you have 2 minus 2, it is 0, and 1 over 0, it goes to infinity. And in this case, 1 minus 4 plus 3, it's also 1 over 0, it's also infinity. So now transform the expression under the sign of the limit. So we should simplify the expression, and we get the following one after simplification. So we have minus 5 over x plus 2, x minus 1, x minus 3. This is the factors of this denominator, two denominators, and x minus 1 and x minus 1, they are cancelled, and we have this expression. And we have obtained the expression of the form constant over 0, because if you put here 1 again, it will be 0. The middle one is 0, because, and it is constant over 0, it means it is equals to infinity. So the answer is infinity. And now, the number 3. Find the following limit. Here we have indeterminate form 0 over 0, because if we put 1 instead of x, we have 1 minus 1, it is 0, and 1 plus 1 minus 2, it's also 0. And now we need to factorize again. X squared minus 1, it's equals to, from short multiplication formulas, x minus 1 and x plus 1. And the denominator is factorized to x minus 1 and x plus 2, because the roots are minus 2 and 1. And we have the following one. They are cancelled, the two of them, x minus 1 and x minus 1. We have just x plus 1 over x plus 2. And now we don't have any indeterminate form, because if you put 1, we get the answer 2 over 3. Number 4. Evaluate the limit. So here we have again indeterminate form 0 over 0. If you put 3, we get in numerator 0, and in the denominator also 0. And again, using the idea of using the common factors, we obtain the following expression. So we have here factorize. If we factorize the numerator, we have x minus 3 and x minus 1. If we factorize the denominator, we have x minus 3 times x squared plus x plus 2. So it means they are again cancelled, x minus 3 and x minus 3. We have just x minus 1 over x squared plus x plus 2. And if we put 3 instead of x, we have 1 over 7. Number 5. Find the following limit. And now, if we put infinity instead of x, we have the indeterminate form of infinity over infinity. So, in order to evaluate the indeterminate form infinity over infinity, we need to divide the numerator and denominator x squared, and then we get, if we divide numerator by x squared, we have 4. So it means for each terms we need to divide by x squared. They are cancelled, and 4, the first one. The second one is 5 over x, and the last one is 1 over x squared. And denominator is 3 minus 1 over x. And now, what should we need now? Now we have the limit of, we can write it as limit of numerator over the limit of denominator. And in numerator we have the second one, and the third term goes to 0 because x tends to infinity. As x tends to infinity, we have here 0 in the middle, and in the third one is also 0. And in denominator we have again, if x tends to infinity, the second term tends to 0, and it means we have just 4 over 3 because these two ones and these ones are 0. And the next one, number 6, evaluate the following limit. Here we have indeterminate form 0 over 0. However, if we put instead of x 2, we have 9. Square root of 9 is 3. 3 minus 3 is 0. And 2 minus 2 is also 0. And now, here we need to multiply the numerator and denominator to the conjugation form of this numerator. So it means this one. Square root of 7 plus x plus 3. Why we need to multiply? To complete the difference between two squares, a squared minus b squared. And then we can cancel the like terms. So here we have the following expression. After this we have this one. Now we can use the formula on top. So it is 7 plus x, square root of 7 plus x squared minus 3 squared, or 9. And then we have 7 plus x minus 9. And hence x minus 2 over x minus 2. Now we can cancel like terms, x minus 2 and x minus 2, and we get the answer 1 over square root of 7 plus x plus 3. And now we don't have any indeterminate form. We can put 2 instead of x, and then we get the answer. If we put 2, 7 plus 2 it's 9, square root of 9 is 3, 3 plus 3 is 6. So answer 1 over 6. Number 7, evaluate the following limit. So here we have again the indeterminate form 0 over 0. And now, similarly with the previous example, we need to complete the difference between squares, select and cancel the common infinitesimal factors. Here again we need to multiply numerator and denominator to this one with plus square root of 3 plus x plus 2. And here one more thing. So in denominator here we have also the square root. That's why we need to denominator also multiply and divide. It means if we multiply and divide denominator and numerator by this square root of 3 plus x plus 2 and square root of 2 minus x plus 1, we get the following one. So here we have it equals to this one, because after division of these two ones, the x minus 1 and x minus 1, which we get after simplifying, they are cancelled, and we have just with minus limit as x tends to 1 square root of 2 minus x plus 1 over 3 plus x plus 2. And then we get the answer. If we put 1 now we have determined form, and if we put 1, we get the answer minus 2 over 4 or minus 1 over 2. Number 8. Evaluate the following limit. Here we have all again indeterminate form 0 over 0. If we put 2, here we have 0 in top, and in the bottom we have also 0. So now we have the formula of the difference between two cubes, a cube minus b cube. So use this formula. We have the following expression: x minus 2 times x squared plus 2x plus 4 and over x minus 2. And now we can cancel them, x minus 2 and x minus 2. We have just this one, the second factor. And then now we can put 2 and we have the answer 12. Number 9. Limit x tends to plus infinity 5 the power of x minus 3 the power of x and over 5 the power of x plus 3 the power of x. So now we can divide by the one of them. For example, in this case we divided by 5 the power of x, numerator and denominator. And we have here it goes to 0 because it's less than 1. The base is less than 1. 1 minus 0, and in denominator the same one. So we have again the base less than 1. So if the base is less than 1 and the power tends to plus infinity, it tends to 0. That's why the answer is 1. And the next one, here difference is as x tends to minus infinity now. And now we need to divide by the 3 the power of x. However, it goes to minus infinity. And then we get 5 over 3 the power of x minus 1. And now, however, this is greater than 1, but it tends to minus infinity x power. So it means it tends to 0 now. And similarly in the denominator also. And we have 0 minus 1 over 0 plus 1, where the answer is 1. So the next one, number 11. I try to collect different examples and more examples. That's why I planned to provide this lesson with in this form. Okay, number 11. Here, limit as x tends to 1 and two fractions. If you put 1, we get infinity minus infinity. This is indeterminate form. And what we need here? We need to give the common denominator. Before the giving common denominator, we can factorize this denominator, x squared minus 1. It is x minus 1 and x plus 1. So we can multiply by x plus 1 here. And we have x plus 1 minus 2, or x minus 1, or x squared minus 1. And now we can cancel them, x minus 1 with x minus 1. And we get 1 over x plus 1. as x tends to 1, and the answer is 1 over 2. The next one, number 12, limit x tends to plus infinity, and this next one. So here we have the power 70 and 30 and 100. So we don't need to open the degree, the power of 70. We just divide by x, all of them, by each terms. And when we divide by x, we have 5 plus 4 over x. And here 5 minus 3 over x. And 5 plus 7 over x. We need to divide each term of this fraction. So then, however, x tends to infinity. This one tends to 0. 4 over infinity, 3 over infinity, and 7 over infinity. So now, what we get? We have just 5 the power of 70, 5 the power of 30, and 5 the power of 100. We can add the powers because we have same base. So it means we have 5 the power of 100 over 5 the power of 100. So it's equals to 1. The next one is the same with this one. Yeah, we can do this example by this way also. So here we can just compute the all terms, all powers of x, and then find this answer. This is same with this one, same example. Okay, now evaluate the one-sided limits of the function f of x at the point x0 is 2. So here, firstly, let's evaluate the right side limit, 2 plus. We also considered in previous topics one example to finding one-sided limits in practice number 5. So here, firstly, we let consider the right-sided limit. So here, 2 plus, and now we can write it like separately to the sum of two limits, and move the limit under the exponent. Then this limit x tends to 2 as x tends to 2 plus 1 over 2 minus x, it is decreasing 1 over 2 minus x, and it tends to minus infinity because this 2 plus. So it means in the right neighborhood of 2, and it goes to minus infinity. For example, this is not correct example, but to explain easily. So, for example, 2.1 or 2.0001. This is nearest to 2 from the right side. It means 2 plus. Right neighborhood of 2. And here we have the value which is greater than 2. That's why it goes to minus infinity. And now, with the second one, we can factorize the second one, and we have x minus 2, x plus 2, or x minus 2, we can cancel x minus 2. And we don't have any now indeterminate form here, and it is just 4 over 2. You can put 2. It's just 4 over 2 or 2. So this one goes to minus infinity. It means 5, the power of minus infinity goes to 0. The second term goes to 2. So it goes to 2. 0 plus 2. This is right side limit. Now consider the left side limit. Left sided limit, it is 2 minus, or we can denote like 2 minus 0, for example. So here again the thing work, and now we can factorize the second one again one more time. They are cancelled, and we have just 2 in the second case. And in the first case now, what we have? In the first case, we have just limit of this one, 2 minus 1 over 2 minus x. And now, this is less than 2 now we have in the denominator. So if it is less than 2, it goes to plus infinity now. So 2 plus infinity, because 5 the power of infinity, it is infinity. So infinity plus 2, it is again infinity. So the left side limit is equals to infinity, and the right side limit equals to 2. So it means there exist left side and right side limits, but they are not equal. It means we don't have limit, two-sided limits. And the next one, so the next part of our lesson, now we'll begin the fundamental limits. So the first one of these fundamental limits, it is theorem 1. So sine limit as x tends to 0, sine x over x equals to 1. This is first fundamental limit. We can say it's like most important limits also. So this is possible. Now let's consider the first example. Limit as x tends to 0, sine 7x over sine 3x. So here we have the expression as 7x over 3x, because from this theorem 1 we can say sine x is equivalent with x. There exists the notation equivalency, and sine x will be equivalent with x as x tends to 0. So it means we can use this equivalency, and instead of sine 7x, write just 7x. Instead of sine 3x, write just 3x. And x are cancelled, and we have just 7 over 3. Or just using this limit, first fundamental limit, sine, here another solution, sine 7x, if we multiply and divide by 7x, so there are no changing. And however, we have in denominator 3x sine 3x. We need to multiply and divide by 3x also. And then we get just sine 7x over 7x times 7x and 3x over sine 3x over here 3x, but 2x are cancelled. That's why we can write that 7 over 3. And here we have the answer. It goes to 1 sine 7x or over 7x, and this one goes to 1 also. And the answer is just 7 over 3. Now, the next one, limit as x tends to 0, tangent x over x. So here we have limit as x tends to 0. Again, we can open tangent x as sine x over cosine x. So sine x over x, it is goes to 1 from the first theorem. And the next one, limit x as x tends to 0, 1 over cosine x. And this one, when x tends to 0, it tends to 1 because denominator tends to 1. 1 over 1 is 1. So the answer is 1 times 1. It is just 1. So therefore we can say tangent x is equivalence with x as x tends to 0. And we denote equivalency by this symbol. Number 3, evaluate the following limit. Limit as x tends to 0, arc sine x over x. So now we can, by changing the variable x is sine t, we obtain t is arc sine x, and t tends to 0 as x tends to 0, because here if x tends to 0, if x tends to 0, here it means arc sine 0 is 0. That's why t tends to 0. Therefore, we have limit t tends to 0. Now we changed our variable. T tends to 0, t over sine t. It is equals to 1 because from, again, first fundamental limit. So those infinite small function arc sine x is equivalent to x as x tends to 0. So we get now 3 ones. The first one, sine x over x as x tends to 0 is 1. Tangent x over x as x tends to 0, it's also 1. And the arc sine x over x as x tends to 0, it's also 1. Now, let's evaluate the next one, arctangent x over x now. Similarly, we can substitute t is arctangent x, imply that x tangent t, and the t tends to 0 as x tends to 0, and doing the same work with the previous example, we have here just x over tangent x. This is 1. So now we get the fourth one. Arctangent x is also equivalent with x as x tends to 0. It's very important, as x tends to 0. Only in this case. Number 5. Evaluate the following limit. Limit x tends to 0. 1 minus cosine x over x squared. So here, by making use of the half angle identity, the numerator can be expressed through a sine function. We will use the half angle identity here. 1 minus cosine x from trigonometric course. 1 minus cosine x is equals to 2 sine square x over 2 with half angle. So from the theorem 1, therefore we need to change this 1 minus cosine x with this one now. Here we have 2 sine squared x over 2 over x squared. And then it's equivalent with x over 2. But here we have squared. That's why x over 2 squared. Hence, we get x squared over 2x squared. It's equals to 1 over 2. They are cancelled, x squared and x squared. It means that 1 minus cosine x is equivalent with x squared over 2. X squared over 2. Because we have here x squared in the denominator. or just cosine x is equivalent with 1 minus x squared over 2 if we move to the right side cosine x and this one to the left side as x tends to 0. The next one, number 6, we'll read this limit. So here, using this identity, tangent x minus 1 is equals to sine x or cosine x minus 1, again from trigonometric course. And we get the following one. Hence, as x tends to p over 4, we can change this tangent x minus 1 with this expression, sine x minus cosine x over cosine x. So, we change it with this one. And they are cancelled. Numerator and denominator, we have just limit as x tends to p over 4 cosine x. This is square root of 2 over 2. Next one, number 7. Evaluate the limit. So, again, we can use the formula, the trigonometric identity. 1 minus cosine t, it's t2 sine squared t over 2, half angle. So, we can change now 1 minus cosine 8x with 2 sine squared 4x because t is now like 8x. And numerator is 2 sine squared over x here. And then we can use again first theorem. It is equivalent with 4x squared. 2 and 2 are cancelled. This is equivalent with x squared. And then x squared and this x squared we can cancel. The answer is 16. Number 8. Evaluate the following limit. So, we have the main trigonometric identity. Here we have sine square x plus cosine square x is 1. Now, we will use this identity. And we have 1 minus cosine squared t, it is sine squared t. And the sine equal with t, we know it. Now, if you replace, so we get this limit in the middle, limit x tends to 0, sine square x over x squared. And if we use the first theorem, first fundamental limit, we get the answer 1. Number 9. Evaluate the following limit. If x tends to 0, it means sine 2x using the first theorem is equivalent with 2x. And tangent 3x is also equivalent with 3x. We considered with tangent also. So, we can replace sine 2x and tangent 3x by 2x and 3x respectively. So, they are cancelled, 2x and x. And we have the answer even we cancel them. 2 and 4, we have 5 over 6. Number 10, number 11, try to do by yourself. This is also not so difficult. They are same with previous ones. Okay, now number 12. Evaluate the following limit. So, firstly, let's transform the numerator. So, numerator here, we need to just multiply with plus and divide by it. So here we have 1 minus cosine x, just because square root of cosine is squared, it gets cosine x. And in the denominator we have 1 plus square root of cosine x. So we consider it, what will be the answer of 1 minus cosine x as x tends to 0. Using the half angle, we get the next one. If x tends to 0, we have 2x over 2 squared, because here we have squared. And in the denominator we have just 1 plus 1. So it means we get the answer x squared plus 4. They are equal with this one. We will doing the examples to infinitesimal and comparing infinitesimal and comparing functions uh, in the next lessons. Also, we will do examples on this topic. We will continue. Okay, now transform the denominator now. So here we have 1 minus cosine squared of x. So it is, when we use trigonometric identity, it is 2 sine squared of x over 2. As x tends to 0, this expression tends to 2 square root of x over 2 squared, using the first theorem. And we get the answer x over 2. The first one was x squared over 4. The top and the bottom is x over 2. Just put instead of the corresponding expressions, and we got the answer x over 2. And x tends to 0. As x tends to 0, it is tends to 0. And now, theorem number 2. Here we have, it is second fundamental limit. Limit as x tends to 0, 1 plus x, the power of 1 over x, it is number e. So the number e is equal to 2.71828, etc. This is irrational number. So, and we can change the formula also. So we can do for infinity here, limit x tends to infinity, and now we have just 1 plus 1 over x. The power of x should be now. So it should be, if we put 0, for example, in this case, if you put 0, 1 plus 0, it is 1. 1 over 0, it is infinity. 1 the power of infinity. It should be in form, in determined form, 1 the power of infinity. And when we change 0 by infinity, it is 1 plus 1 over x. 1 over x tends to now 0. And here just x. So it means again 1 the power of infinity. Here the same example which I said about it. So limit x tends to infinity now, not 0. Look here. Here we have difference between them. So we can change 0 with infinity, and then it changed the expression also. So now here x plus 4 over x, it means we can divide by terms. X over x, it is 1, and 4 over x. The power of x. So now they should be same with this one, with this in the inside of this brackets. So here limit as x tends to infinity. Here 1 plus 4 over x. Now we will multiply and divide by 4 the power. So it is x over 4 times 4. But here it gives to us just number e. Look here. Because limit x tends to infinity, 1 plus, we can write 1 over x, the power of x, but here we have 4 and here also we have 4. We transform to this formula. And now this is number e. So we have e the power of 4. The answer is e the power of 4. Number 2. Evaluate the next limit. So here we can divide this expression by 2 polynomials. 1 plus 3 over x the power of x, using the property of exponent. And here 1 plus 3 over x the power of 2. So in this case, if x tends to infinity, the second one is tends to 1 because of 3 over infinity here. It is 0. 1 plus 0 is 1. 1 squared is just 1 again. And now we have the first one also. So here again, one more time, we need to divide and multiply by 3. And it gives the second fundamental limit. And hence we have the answer e cubed. Evaluate the limit, number 3. So you can see we will do the same operation as the previous one. So, but the difference is here we have minus in the middle. That's why we need to write minus in the power also. Because of this one is now your, how to say, your second term. The first term is 1 to use the formula. And then it means this one gives to us number e, this bracket 1 minus 4 over x, the power of minus x over 4. This is number e, and number e, the power of minus 4 we get, or 1 over e, the power of 4. Number 4, evaluate the next limit. Limit x tends to infinity. Now, x plus 3 or x plus 5. So, how to solve this example? To solve this example, we need to divide by x inside of our brackets. So, then we have the following one. 1 plus 3 over x, 1 plus 5 over x, the power of x. And now we can evaluate them separately. Limit x as x tends to infinity, 1 plus 3 over x. Now, again, divide and multiply by 3. We have e cubed now. In the bottom, we have the similarly e the power of 5. So the answer is 1 over e squared. Number 5, evaluate the next limit. Limit as x tends to 1. So now you can write in this form: 1 plus 2x minus 1. If you open the bracket, we get 2x minus 1. And now we can use the second fundamental limit. Now we had a form of this limit. But we need to divide by 2 to the power of x minus 1 and times 2 to the power of x minus 1. So what do we get here? And then it gives to us just 1 plus this one, the power of 1 over 2x minus 1. This is number e. Inside is e. And e to the power of 8x, as x tends to 1. It means e the power of 8x, or just e to the power of 8, as x tends to 1. Now, the next one, Theorem 3. We can say this one is just corollary of the second fundamental limit, or consider separately with them, with this one. So here, limit natural logarithm 1 plus x over x, it is 1. Let's consider the first example. Evaluate limit x tends to 0, logarithm 1 minus 2x over 7x. So what should we do here? Let's use the formula. Let's use the theorem 3. So we can multiply and divide by 2x minus 2x. And then they are x and x, they are cancelled. But we have this form now. And before the limit, we have constant minus 2 over 7, because we multiply by 2 and divide by 2. And it gives, this limit gives just 1 using the theorem 3. That's why the answer is minus 2 over 7. Number 2, evaluate the following limit. Logarithm 1 plus sine 4x over tangent 2x. By theorem 1, from the first fundamental limit, sine 4x is equivalent with 4x, and tangent 2x is equivalent with 2x, as x tends to 0. And in addition, we have natural logarithm 1 plus sine 4x. This is equals with 4x, because we need to divide by sine 4x, and then we get 1. That's why we call it, they are equivalent. And sine 4x is equal to 4x, as x tends to 0. Therefore, we have 4x over 2x, or just 2. Number 3, evaluate the following limit. So let's try to do by yourself. This one is also. So number 4, evaluate the limit. So here we will use the property of logarithm. Logarithm minus logarithm, it is logarithm a minus logarithm, it means logarithm a over b. So here we have x plus 2 over 2, or by this way we can write And however, 2 over x is an infinitesimal function as x tends to infinity because it tends to 0. Then natural logarithm 1 plus 2 over x is equivalent with 2 over x. Therefore, we have just put instead of this one 2 over x and 1 over x and x are cancelled. The answer is 2. Theorem number 4, the next one, this is also corollary from the second fundamental limit. Now, limit x tends as x tends to 0, e to the power of x minus 1 over x is equals to 1. First one, let's do the first example. Evaluate the limit. Here we have 2x, e to the power of 2x. But in this case, we have just x, and here it should be x. So, what should we do? Yes, multiply by 2 and divide by 2. And there is no changing when we multiply and divide by the same expression. So, the answer is now e to the power of 2x minus 1 over 2x as x tends to 0 and coefficient 2. So it tends to 1 now, this limit, using the theorem 4. And our limit tends to 2. And next one, limit x as x tends to 0, e to the power of sine x minus 1 over 4x. So e to the power of sine x minus 1, it tends to sine x as x tends to 0. Look here, because we have e instead of x, just sine x. And there should be also sine x. So this is numerator is sine x, the top is sine x as x tends to 0, and the bottom is 4x. So you can write by this way, 1 over 4, just write as coefficient, limit as x tends to 0, sine x over x. And from first theorem, it goes to 1, so the answer is 1 over 4. Evaluate the next limit. Firstly, e to the power of square root of x minus 1 is equivalent by x, and tangent x is also equivalent with x as x tends to 0. Second, x is an infinitesimal function of a higher order. Hence, we have the following one: square root of x plus x is square root of x as x tends to 0. So here it should be, in the numerator should be, it is square root of x, it tends to square root of x, square root of x plus x, it is again square root of x as x tends to 0. And tangent x is equivalent with x just. So square root of x over x, it means 1 over square root of x, or just plus infinity when x tends to 0. Number 4, evaluate the next limit, e to the power of x minus e, x squared minus 1. So here also we can do the substitution. Here setting t is x minus 1 and noting that t tends to 0 as x tends to 1, we obtain e to the power of t plus 1, just replace x with t plus 1, t plus 2, e to the power of t minus 1, t plus 2. So then we have just, if you put t, we can write separately these two factors, e is coefficient, limit t tends to 0 et minus 1 over t, and limit t tends to 0 1 over t plus 2, and then we get e. The first limit tends to 1 from the last theorem, and the next one is second one tends to 1 over 2 when t tends to 0. We don't have indeterminate form in the second one. So the answer is e over 2. Theorem number 5. For any number n, we have the following equation. Limit as x tends to 0, 1 plus x the power of n minus 1 over x, it is n. Let's use this formula and solve the next examples. Example number 1, here evaluate the limit as x tends to 0, square root of 1 plus 3x minus 1 over x by this theorem. Here we have case n is 1 over 2 because we have square root. So, and to do in form, we need to again multiply and divide by 3 here. So, and the answer is 3, limit this one, and this is goes to now n is 1 over 2. So the answer is 3 over 2. Number 2, evaluate the next limit. Again by this theorem, theorem number 5. Here we have the case n is 1 over 5 and sine x is equivalent with x as x tends to 0. And we obtain the next one. So here we have minus 1, but in this case it is minus 2x, not plus x. That's why we need to divide by minus 2x and minus 2x and multiply by minus 2x. But however, sine x is equivalent with x, so we can change sine x with x, and we don't need to multiply by x. So the answer is minus 2 times 1 over 5, because this is now the form of theorem 5 and it's equals to n. And in this case is 1 over 5. The answer is minus 2 over 5. Number 3, evaluate the following limit. Limit x as x tends to 0, the cubic root of 1 plus 4x minus 1, and the bottom square root of minus 1 minus 7x minus 1. So again, using the theorem 5, first in the top n is 1 over 3 and in the bottom n is 1 over 2. So we will try to solve it separately, top and bottom. And if we calculate the top, it tends to 1 over 3 if we multiply by 4 and divide by 4x I mean. And the second one, it's also the same situation. So here we need to multiply and divide by minus 7x. So the first one tends to 1 over 3 and the second one tends to not 1 over 2 because this is, we write inversely. So that's why it is just 2. And just put instead of these two expression, we have 1 over 3 times minus 4 over 7 because we need to multiply by 4 and here by 7 and divide by them. That's why here we have coefficient minus 4 over 7 times 1 over 3 times 2 because this limit tends to 2. And the answer is minus 8 over 21. Number 4, evaluate the next limit. So here we have 2000 second degree in top and in the bottom also the same. So how to solve this example? Here it's again, so this is just n, it should be n if you use the theorem 5, but here should be 6x. That's why we again one more time multiply and divide by 6x, and in this case of the same situation, so minus 3x it should be multiply and divide by minus 3x, and the answer it goes to 2002 and it goes 1 over 2000 because this is inverse 1 with the formula. That's why here we have just minus 2, the ratio of minus 6 over 3. And there's two limits. And the answer is minus 2 times 2002, 1 over 2002. They are cancelled, 2 ones, and we have the answer just minus 2. Okay, number 5 and number 6, try to do by yourself. So, I think it was clear today, the examples. We will continue the next time the topic limit of functions, especially we will consider Landau symbols. And it was last example for today. Thank you for attention.